Hello, my name is Greg George, and today I wanted to make a presentation. This is a presentation that I've used different various forms of throughout this year at different trade shows for presentations and breakout sessions. And I figured I would go ahead and take this presentation and record it for use on different outlets, whether it's social media or sharing with people that are interested in reverse engineering or product design or scan-based design, we sometimes call it. So that's what the purpose of this presentation. It's a little bit different than what I normally do, where I load up the product and do a technical presentation. But I wanted to do this because there are two big hurdles when I'm using or presenting our software in the marketplace. Two of the biggest hurdles are one, people have no idea what it is and why they would even need it, right? There's a lot of confusion on it. And the other one is stems from that is that if they do find out or discover their need for a product along the lines of our software products that we're going to talk about today, they usually have like pretty unrealistic expectations as to what's possible. Um, and I'll get into that a little bit more in the future of this presentation, but we'll get into that. So I just, this year I spent a lot of time essentially kind of evangelizing what this process looks like and just telling the marketplace over and over again because there's a lot of confusion surrounding reverse engineering and product design. And then the other one is showing a realistic expectation of what can be accomplished with softwares like what we make. So that's kind of the purpose behind this presentation is to kind of give you examples and talk about the how and the why as well. So let's just go ahead and jump in. I spent enough time talking about it. I always do this real quick. Who is Octon? As many people know, if you're in the Geomagic, if you're looking at Geomagic stuff, we're a scan-based software where we built groundbreaking software at the very beginning of the industry to be able to take large data sets from the different types of scanners that exist in the market and built softwares around those. And Geomagic's name's been out there forever, and 3D Systems acquired it many years ago. And we've kind of been this group inside of a 3D Systems, a 3D printer company. Well, they also acquired a company called Octon. Octon is a manufacturing OS that specializes in mainly AI type uh, MOS functionality. So it's this cloud-based MOS that connects to MES, IoT, and CAM, and robots, and all kinds of stuff. And what they did is 3D Systems took us and split us off into our own group. And now we're this one separate third party almost software group. So we're a hardware neutral company, whether it's scanners or CNC softwares or printers, different devices on there. We work with everybody. That's the goal here with the operating system, right? And the same DNA is in Geomagic. We've always been this hardware neutral company that wanted to connect to everybody's software, everybody's hardware. So that is who Oqton is. It's the subsidiary, not necessarily a subsidiary. I don't think I'm allowed to say it's that, but it's a group. 3D Systems still owns us, but we're this group off to the side that makes software, manufacturing OS software, the Geomagic suite that many people already know, and then we have some 3D printer and DICOM software. So let's jump into the products. I'm just going to explain what some of the products are that we make. Geomagic Design X, which is the main one I'm going to talk about today. It is our ultimate scan to CAD solution where we're taking scans from different devices and getting that data over into usable information for manufacturing, whether it's CAD or CAM or whatever. We'll talk about a little more about that. What we did is we took some of those tools and put them inside of SolidWorks. So that second product is that we have some of the tools from DesignX and we put it inside of SolidWorks for those users. It's a subset. It's not everything that we have. And we also have to follow the rules inside of SolidWorks as to how it works. So there are some limitations there, but it's great to be able to bring scan data and work with it inside of SolidWorks. And then Geomagic Wrap, we've had this software forever. Its main wheelhouse is three main areas. It's very good at scan and mesh scan editing. It's amazing at that. Second, it's very good at fitting surfaces to the geometry, like drawing surface patches on it and fitting those. And then the third one is it's has its own essential API to it, so you can actually write your own scripts on top of Wrap. So it's very neat. It's almost like this 3D scan engine that you can use. So those are the reverse engineering. And then we have quality control software. So you scan stuff with reverse engineering to recreate it. With quality, what we're doing is scanning it to compare it back to the CAD model to inspect it or make dimensions. So we have Geomagic Control and Control X Essentials. So those are two levels or tiers to that product line. So I'll make videos on that in the future. But for today, I wanted to jump in. This is kind of the start, the meat of the presentation here is um, the why, like why people are doing scan-based design or reverse engineering, right? So many years ago, there is an introduction of 3D scanning devices into the market, different digitizers out in the market. So you see here we got arms and white light scanners and laser-based handhelds, structured light scanners. All of these have been around for many years, right? We created those so we can capture the shapes of different objects and get them into the digital world, so then we can do different things with them. In this presentation, the focus is recreating them or reverse engineering them. And where people want to go with those, that data from those scanners is over to either three kind of main categories, is the way I break it up in this presentation. The top one is they want to get it into CAD. That's probably one of the most common. So once you get that data into CAD, you can create your drawings, assemblies, put it in your PLM database, and then integrate it into your complete manufacturing workflow. The second one is sometimes people want to go straight to the CNC package itself and just cut another one. Like small job shops, um, large companies too may want to do that as well, but just go straight to the CNC. And then the last one is scan for additive. So scan and get the data over into an additive solution to print, essentially print that or duplicate that object from there. But historically, this has been a problem. You can get there, but there are lots of long roads in there because there aren't many softwares that get you from here over to here very efficiently. So that's exactly why we created Geomagic Design X. Its focus is to take that data that comes from all these different devices and operate with it as native geometry and extract what you need. It could be a parametric model. We'll talk about some of the deliverables. It could be just surfaces, and get exactly what you need to send it to where you need to go, whether CAD, CNC, or additive. So it should be CAD, subtractive, or additive. You could define it that way. And get it to where it needs to go. And that's what we made DesignX. DesignX is essentially a CAD platform. We took a CAD kernel and we took our scan processing kernel that we built natively in-house over the course of 25 plus years of R&D and development. Again, so with our developers, they are some of the first people to ever do some of the scan processing techniques that we have. We've been in the industry forever. Many, many people know us. So we put that platform on top of a CAD kernel because that's what CAD is missing. People want to get to this or something like this, but CAD still to this day treats this like a foreign object. CAD packages are adding tools here and there every once in a while to make it a little bit easier, but as you will see, if you start to go down the road of reverse engineering, you'll discover that it's missing a lot of tools, and that's where DesignX comes in. We're giving you those missing things in between the scanners and the deliverables here. So that is the industry problem that's been out there. Now, here's some of the granularity on the types of information. This is the nitty gritty on why we're doing it, because there's different types of 3D models. Sometimes I call them 3D model families, right? So there's different types of representations of 3D models inside of computer software. These are a handful. These are not a list of every single possibility that's out there. These are just my 5 most popular ones that I run into in the market today. So I'll just do a brief explanation as to what these are. I find that if people understand what these are, they're more intelligent. They're able to figure out what it is that they need if they kind of understand the nuts and bolts of what these different scanners are giving you and where you need to go. So on the left-hand side, this is a very simple. This is like the most basic rudimentary version, a point cloud. So a point cloud is just a group of 3D measurements, X, Y, Z points in space that are graphed, right? And in this instance, you'll see that those points are all black. But sometimes those point clouds can also have IJK direction vectors as well, which will allow us to shade them more appropriately and make it a little more sense to look at in 3D here. And then they can also have intensity values, RGB values. There's all kinds of other values that can be on top of those point clouds. So a lot of the devices actually collect this information. It's just a very large group of dimensions that are all closely related to each other. They're just in close proximity. You have so many of them, you can see a picture of what the image looks like, or the 3D image. The next one is kind of a variation of the point cloud. The best way to describe it, what our software does, is we will take these point cloud and we will connect those measurements together, the closest measurements together, into triangles. So like you see here on this image here, that is the simplest way to connect those dimensions together is into the triangle form to represent the shapes. And what that inherently does is it's a smarter, more intelligent type of 3D model that is then becomes a polygon surface. It's easier to shade, it's easier to render on screen. It's actually the type of model that all software, even CAD, uses to display the models on screen anyway. So polygon meshes are very efficient at for display purposes. So we're connecting those vertices or 3D dimensions into triangles. So it's kind of like another level of intelligence on top of a 3D point cloud. That's the way I like to describe it. So these are kind of in the same category. They're relatives of each other. Now, a very, very distant 3D model type that has very little to do with the polygon mesh and point cloud is the CAD model. CAD models are made of NURB surfaces, non-uniform rational basis spline. So that is a type of math that is used to represent 3D shapes inside of software. The benefits of this is it's very easy to apply formulas and dimensions and make these editable because they are parametric in nature. So they're parametrically driven. You can adjust parameters of different types to adjust them to make things flat, perfectly cylindrical, apply a dimension from here to here, all of that stuff. So there's lots of intelligence in CAD. And most of the time, CAD models are created from a blank screen where a designer or engineer will create these from scratch, right? And there is no current way of taking a scan and just having it automatically convert over to a CAD model. Now, there are assisted tools, which we'll get into in a little bit, to help us get there and make it a lot easier. But right now, this CAD models is the family that drives manufacturing around the world. There are There are ways of manufacturing off of these too, but by far this is the most popular model type used in manufacturing today. So the majority of people want to get over to this type of model. And again, this is what DX solves, which we'll get into here in a second. Now, two other ones that I'll cover really fast. Subdivisional surfaces. These are a surface type that's used a lot in animation and the AR VR world. Different types of representation in the world. What these are very good at is push-pull modeling. They represent stuff. Subdivisional surface models is what you'll hear them called. Um, they're kind of like a hybrid in a way. I think of them as having a NURB surface that's controlled by a polygon outer uh, armature or frame that helps pull and push and create shapes. Again, used in AR, VR, and animation. And then voxels has been around for a long time. Very few softwares utilize them. Our freeform software uses them. It's essentially volumetric pixels. So they're very similar to these, but the points here have zero volume. These actually have a dimension. So what you can do is in this arm example, all the voxels are so small. They're like grains of sand, except they're cubes. And, they may be set to a zero point 0.1 millimeter size, and they represent this shape with volumetric pixels. So that's another type you may run into. Now, when you start looking at recreating or rebuilding a model, you have to think about what you're trying to get out of it. Are you trying to create an exact representation of that object, or are you trying to create a perfect version of it that then you're going to model off of? So I'll give you some examples here. On the left-hand side, I use an extreme example of taking a 3D scan of somebody's anatomy, and then we have a tool that will allow you to wrap those NURB surfaces, those non-uniform rational basis splines, around the outside of the arm and create an exact representation, almost exact, with very little deviation, within thousandths, some microns of the original shape. And you can control that. You can add more or less resolution to it if you want. So that's an example of like, I want to create an exact representation of that person's anatomy. Maybe I want to make a brace or something that goes around the hand that I can use as a controller, or, there's all kinds of different reasons why you might want to make something that fits to somebody's anatomy. That's what we call as built, or existing, exact duplicate as close as possible. The second option here is, with a mechanical part, if I 3D scan the shape and I measure between those holes, let's pretend like the distance between those holes is supposed to be 3 inches. If you scan a part or measure with a CMM or a pair of calipers or anything, you can grab those calipers and make a measurement from hole to hole. It'll never be 3 inches, right? Because there are tolerances built into manufacturing. There's error, and every step there's error. It may be very small amounts of error. The devices that we build today are very accurate, but it will never be, almost never be, 3 inches. If it is, then you need to play the lottery. So what you need is, I don't want to duplicate the part with the tolerances or error built in. Actually want to create a model of the part that is the design intent, or what it should have been, right? And this is another thing that DesignX does extremely well. So that will allow me to model around the part, pull the dimensions, and override them to be what they should be. That way, when I make another one, I'm not stacking the tolerances of it from when it was made before on top of the new tolerances of what it's going to take to make another one, right? And then the last one is, why not both? There are instances where you want most of the shape to be as built, and in some of the shape to be design intent. So you can combine them together. And I use another extreme example just to demonstrate how we might have this very organic shape that was calculated through simulation, and I want to wrap CAD surfaces around it, but I do want to control where those hole locations are very precisely. And you can do both of those inside of DesignX, which is very powerful. So the deliverables that the main categories of deliverables that come out of scanned data are on the left-hand side. You can just scan it and go straight to a mesh, just like we talked about. You can connect those points, the vertices from the point cloud together into a mesh surface, and 3D printers will read that mesh type, the STL type, PLY file type, OBJ. All those will be read into different slicing software for additive manufacturing. Very simple workflow, right? But that's going to create an exact duplicate. It's going to represent, I can't make changes to those whole locations with meshes. The next one is quick surfaces. Maybe I want to run a CNC toolpath across this. Well, most CNC softwares will not run toolpaths across mesh surfaces, but they will off of non-uniform rational B-splines or NURB surfaces. So we can wrap those quick surfaces around a mesh and then take it over to a CNC software and output a toolpath to be able to cut that hand, right? And then the third one, which we talked about when we talked about CAD, is feature-based CAD. A lot of people want to scan an object and create a fully featured editable CAD model that I can then manufacture off of. And then if I ever need to change dimensions or move things around, it's fully editable and you can work with it. And then the last deliverable of the highlights here is the hybrid model deliverable. So you can combine the feature-based and quick surfaces like we just talked about. So these are like 4 different examples of deliverables, and I talk to customers every day, and when I consult with them, I'm just listening for what they want to do, and then I'll categorize them in one of these groups. I will say the majority of people, this is kind of the holy grail. This is where people want to get, and this is the hardest one to do. I say hardest, it's not extremely difficult, it just takes the most amount of time. So now that we talked about different deliverables, let's kind of talk about actual applications, what people have done. So this right here is kind of like a highlight reel, just talking about high level reasons why people reverse engineer in the marketplace. And you'll see what I mean once I go through a few of these, why people are reverse engineering. And my hope is if I show people what I've run into over the years of doing this, that it'll kind of open people's eyes to what is possible once you have this software and scanners in front of you, the different type of applications you can utilize. And hopefully that will birth new ones in the future because you get more people involved in this world. So to start off with, on the left-hand side, I use a guitar as an example. Many times there are handmade products out there in the marketplace. Maybe it's not a scan of a manufactured piece. Maybe this is a handmade object where that guitar sounds a certain way because it was made out of a certain kind of wood and it has a certain shape to it. And there's just a certain DNA to it. It's been made that way forever, and we figured out that it works. It's amazing. If you scan and digitize those handmade parts, you can capture that handmade craftsmanship and digitize it to then duplicate it and mass manufacture those pieces. So creating a digital version of a physical part, and I would even add, handcraft it. The second option is this is a body from a off-road vehicle, or it could be a race car or a side-by-side, a bunch of different vehicles here. You need to add a roll cage to it, right? The old way would be just to have a fabricator go in and just eyeball stuff and hold up a pipe and weld it down and hold up a bracket, cut it out and make measurements and try to design around the shape. Well, we can actually take a scan of that entire shape, design in 3D a full armature network of roll cage to it, actually plan out where the mounting points are, manufacture it, and even simulate how the pieces will go in and out and where they need to go. So you can design around an existing part. That's essentially it. When we say I want to 3D scan something, people are usually thinking I want to scan that part to duplicate that part. Sometimes you're scanning a part to design around. And that leads to this next one. Many times you'll design one part to design another one as part of an assembly. So that's all that one is. It's just a simple representation of a ball joint where you want to design mating pieces to an existing piece, right? The fourth one here, very simple one, but it's often overlooked, is just archival purposes. If I 3D scan that object, I have that object preserved in 3D forever, right? As long as I don't lose track of the file, I can back this up and I have that shape preserved. So if I ever need to make another one, so archival purposes is great, and it's also great for manufacturing. I use an example of a statue there, but manufacturing, there are lots of companies out there that have legacy parts that they have a physical copy of that they may need to make them again in the future. And if that factory burns down or lost or those parts get destroyed, they will lose them. And it would cost a lot of engineering time and money to start all over and create those designs from scratch. So archival of mechanical parts is important as well. For the second slide here, um, capture real life models for simulation purposes. So that's another reverse engineering application that we see quite a bit. This exact one is scanning somebody with a handheld scanner on a luge and then running simulations so they know how to change designs, uniform, helmet, like all that stuff to squeak out every millisecond out of their luge runs. So design for simulation, scan actual people. I actually took CT data from somebody's head once, and they did simulation on their nasal passages once because they were trying to figure out what was going on with this specific person. So they were able to run the simulation, and you could even make changes digitally to figure out if we did a surgery, what would it change the results of the simulation, right? So you can use the simulation for medical as well. Scaling models. So this is a very basic one. Scan a maquette of a design, scale it way up, and cut it in separate pieces to manufacture. That happens all the times with all the time with large sculptures. So that's a pretty simple one, but really powerful. This is one that is amazing that we work on quite a bit for the turbine blade and aircraft industry. So they have many, many, many of these blades out there, and every micron of accuracy could be potential loss of millions and millions of dollars, right? So if you scan one of these blades, and maybe that was the blade made on a Friday before the holiday, before the new year, or whatever, that could have been the worst example of that blade that you selected to scan and reverse engineer. So why not scan a large group of them and average them together so you can get a better representation of what that part should have been? And we have those tools in our software where you can actually average parts together and even average linear or circular arrays of the parts, and it will overlay them automatically and average them. So that is a really powerful tool. Another one is just flattening. So if you need to, in this example, a spool valve or even die cutters in the printing industry or upholstery, fancy upholstery for automotive or whatever, you can scan the shape of the part. You can lay out. In this instance, we rolled out the design because it's easier. It was probably designed in 2D to begin with and then wrapped around. You can better reverse engineer that shape by unrolling it and then creating a more accurate design. Broken parts, this one's kind of obvious. If a lot of dies and stamping, the parts will break. You know, they only have a couple of them, and this goes back to the archival purposes. If you scan it ahead of time, you'll have that on hand to be able to work with. But we can scan the pieces and put it back together digitally and then reverse engineer. This other one is a new one, AR, VR, and CG. Scanning to get representations of real life objects into the digital world for either AR, VR, and CG. CG has been doing this for a long time with movies. They'll scan city blocks, all different kinds of objects, props, and everything, and get them into the software digitally to use for animation. Actually, use it for alignment of different camera angles to make sure the real life shots match up with the CG shots very accurately. So they use scanning all the time, and that's reverse engineering too. Aftermarket parts, where you're designing your parts to fit different pieces. out in the market. Everyone knows of the WeatherTech example. So, you see those commercials with the laser scanner scanning pieces and then creating parts to mate. Project planning. This one is huge. I use an example of like the power gen world. They will scan the entire factory to know where all the pipes are, all the facilities, and do all kinds of project planning and monitoring. And they even bring it into the BIM world so they can label everything and have reports and know how much of this kind of pipe or whatever. But they also use it for project planning. So if they're going to have an outage, they can actually simulate, will this tank fit out of the door? And what's the best way to manipulate it to get it out that door? And do we need to build a frame or a cart to hold it? Right? So you can use the scan of the entire facility to simulate your outage and save lots of wasted time in those types of applications. Medical, medical braces and fixtures. That's why I use that hand. We do a lot of this with freeform. That is reverse engineering as well. That's an example on screen of a design that we made to create a brace for somebody's uh, anatomy. And that's an example where we did not use NURB surfaces or CAD. We actually designed right off the anatomy using the voxels. Voxels can be extracted straight from meshes and point clouds, and you can create designs and do like CAD modeling on scans. And we do that all the time, creating big fixtures and guides and all kinds of different things for the medical industry. Forensics, this is exploding this market where they're actually giving scanners to the different law enforcement groups. They're able to scan an accident or crime scene, capture it, clear it, and get everyone back to normal and back and up and running. And then they can go back and simulate and make dimensions and even recreate with animations to see what happened, or even take that stuff into court and use it as evidence. Topology optimization. So in this instance, you can create different topology optimized parts. I think many people are aware that we're using simulation to create topology optimized parts, but the output of those softwares is usually polygons. So we can take those polygon models and clean them up and wrap surfaces around them and use that hybrid approach that we talked about before to then extract a good CAD model from topology optimized processes. And the last one here is this is one that I discovered by visiting some manufacturing. There was a manufacturer that did some stamping, and they'll do a design for a stamp, and then they manufacture that expensive tool, and then they roll it out, and they start stamping out test parts, and then they dimension them. They do their first article inspection. When they do that, they discover that, oh, if I add a little material here or I round off this fillet edge just a little bit here, it'll help create a better part. So there are, you know, people on the floor, whether they're engineers or people running the tools, that over time will make changes to make that or tune that stamp to create better parts for things that we can't necessarily predict, right? How the material wraps around the shape or whatever. But what happens is that change isn't documented and rolled back into the original CAD model. So we've had examples where we have customers scan their dies that they know are making phenomenal parts. Like this die, for some reason, is making great parts. They can scan it, they can overlay it with the CAD model, see where it's been changed, and update that original design so that way if they ever have to make another die, they can start from a better starting point. So finally, I'll get a lot of people asking me, look at my parts. Do I really need a 3D scanner and software like this to reverse engineer my parts, right? Sometimes there are people that have an application. It's kind of right on the line, right? And this is kind of where I go with that question is how complex is that part? If it's just a 1, 2, 3 block, obviously I can measure that with a pair of calipers and model it in CAD faster than I could even unpack my scanner. But as the complexity increases, the more time you're going to save. And I give examples here at the bottom. You got this basic little valve here at the bottom. You're still saving time because while that's a very simple model, there are hundreds of dimensions that you need to know in order to model that accurately, right? And the other thing is 3D scanning provides you feedback. That's why I use these 3D color plots on the surface there to show that as I reverse engineer, I can compare back to the original scan and make decisions to understand if I want to make that hole size, a 1 inch diameter, and compare it to the scan and see if that's what it really should be or not. You can catch a lot of errors. You can make a lot of decisions along the way that save so much time within the reverse engineering or design process. So as you move up that scale, you're going to save more time. And that's kind of what I use to determine what product I use sometimes or whether or not I need this. Um, how much time I'm going to save? Is it really going to add a lot of value? And most of the time, it is actually. Once you learn how to scan and reverse engineer stuff from scan data, it's really, really valuable process. So that is my presentation. Again, this is more to kind of talk about the why and talk about the how and give examples of how people went about this in the market and what's possible to get everyone thinking and just kind of evangelize what reverse engineering or scan-based design is, um, and then hopefully collaborate with new customers on some amazing applications. So thanks a lot for watching this presentation. Hopefully it was informative to you and helps you out. Thanks a lot.